Okay, muscle contraction. So we have established that the neuron, what it's going to do is it's going to stimulate the muscle to depolarize. And that depolarization is the action potential. And the action potential is going to travel down the sarcolemma. It's going to travel down the T tubules. The T tubules are going to depolarize the sarcoplasmic reticulum, and that's going to open calcium channels. All right. Okay, so we've established that so far. So let's do it again. So acetylcholine is released by the motor neuron. Oops. Motor. Why is it not writing? All right. Motor neuron. Okay. The motor end plate is going to depolarize. Okay. The action potential is going to travel down the T tubule. Calcium channels are going to open. In the sarcoplasmic reticulum, and then we're going to release calcium into the sarcoplasm. Calcium is going to initiate contraction. Okay. This contraction is sustained by ATP. Okay. If we have calcium in the sarcoplasm, if calcium is in the sarcoplasm, and if it is bound to troponin and ATP is available, the muscle fiber will shorten. So these are the conditions. If calcium is floating in the cell freely, bound to troponin, and ATP is available, we can shorten the muscle. We can contract. Okay. All of these molecular events happen in the sarcomere. Okay. So basically what this means is I've got a Z disc right here. There's my Z. I've got a Z disc over here. Got the M line over here. Actin moving in this direction. Actin moving in this direction. Myosin in these directions like this. Okay. Calcium is binding to stuff here. Calcium is binding to, remember, it binds to the actin. And all of these events that are occurring, okay, actin binding to myosin, is occurring in the sarcomere. It is the sarcomere that is the actual functional part of this. Okay. And what eventually is going to happen is the Z discs are going to move closer together. That is what the goal of this is, to get the Z discs to move closer together. And that's going to cause a contraction. That is a contraction. It's not the cause of it. That is a contraction itself. All right. How does it relax? Okay. So a muscle will relax automatically when the nerve stops stimulating the muscle. Okay. What that's going to make, what's going to happen is the sarcolemma will repolarize. Okay. The T tubule will repolarize. Okay. The voltage gated calcium channels are going to close. V gated calcium channels. In the sarcoplasmic reticulum, they will close. Calcium will be pumped back into the sarcoplasmic reticulum. Okay. The lack of this calcium will cause tropomyosin to cover myosin binding sites on actin. Okay. And that's it. The muscle will relax after this. You don't just have to have a removal of calcium also to cause muscle relaxation. If you have a depletion of ATP, the muscle can also stop contracting. And what this is called muscle fatigue. Muscle fatigue itself. All right. Now we're actually going to get into the nitty gritty of this, how it actually works. Now, when stimulated by a motor neuron, when you stimulate a muscle with a motor neuron, the end result will be, if you have calcium and if you have ATP, is that the actin is going to be pulled over the myosin in the sarcomere. So what's going to happen is it's going to move in this direction, and this actin is going to move in that direction. That is going to be the end result. The end result. Okay. Now, it can only happen when calcium exposes the myosin binding sites on actin. Okay. That's it. It can only happen. You can only get this contraction. You can only get the movement when calcium exposes the myosin binding sites on actin. Okay. So calcium will bind to troponin. Okay. So that tropomyosin can expose the binding sites on actin. All right. So let's say this again. Calcium will bind to troponin. And what troponin is going to do is it's going to move tropomyosin so the binding sites on actin are exposed. Now these myosin binding sites that are on actin are they're very attracted to myosin, and they'll bind almost instantly. And what this does, when you have actin and myosin bind together, this forms what's called a cross bridge. Forms a cross bridge. Okay, and what this cross bridge does is it allows the myosin head to pull the actin toward the M line, the center of the sarcomere. That's what it does. The short distance, and it's really short, it's like 5 micrometers. It's really, really, really tiny, really, really tiny. And so basically the myosin has to let go and reattach itself to the actin so it can keep pulling the actin. And the thing that we need for this is ATP. So that's where ATP comes in. ATP is necessary to let myosin release the actin so it can reattach later. So that's the sliding filament model. Basically, what the sliding filament model says is that myosin pulls the actin over. That's what the sliding filament says. Everything else is the mechanisms of the sliding filament model. Now, how does ATP work? Okay, so the act of pulling requires the myosin heads to attach to the actin, pull the actin, detach from the actin, and reattach to the actin so it can pull it again. And what this is attachment, pull, detachment, reattachment. This is all called the cross bridge cycle. Okay, and this cross bridge cycle, it requires ATP. You got to have it. If you don't have ATP, you can't make cross bridge. Okay, so how we do this formation, the release, and the power stroke is first, step one, the myosin head has to attach to actin. Okay. Now, when you do this, what we're going to do is we're going to start here. We're going to start right here. That's how we're going to do. So we're going to attach to the actin. We're going to attach that. So we're going to assume that calcium has already been attached to actin. The myosin is going to attach to the actin as well because we've exposed the binding sites. Now, we're going to make an assumption that ADP and inorganic phosphate, that's what that P(i) means, inorganic phosphate, they're still attached to the myosin. Okay? Now, the first thing that happens once we do this is the inorganic phosphate is ejected from the myosin head. And what that's going to do is it's going to strengthen the cross bridge. So what this means is it makes them attach even more strongly. Okay. Now, when you do this, you're going to perform a power stroke. The power stroke is going to occur. And what the power stroke is where the myosin pulls the actin. That's what it is. It is the pulling of the actin. So this is the pulling of the actin. So that's what happens in the power stroke. Okay. And then what's going to happen is the ADP is going to be kicked off. So now we've got actin bound to myosin and nothing else is attached. Okay. So that's it. Now it is irreversible. They're irreversibly bound until ATP reattaches to the myosin. And then what's going to happen is the myosin is going to hydrolyze the ATP, which means it's going to break it. And that's going to allow it to release. going to allow it to release from its old position, recock itself, and reattach. Okay, so that's the role of ATP in the excitation contraction coupling. And hail went way long, so I'm going to stop it here, and we should only have like one more, and then we'll be done.